Good morning. I wish I was him. I've given many lectures in my life, but speaking for a professor of mathematical modeling is a bit challenging for me. I'll try to do my best to represent him. Good morning, everybody. I have no disclosures. So all of you know that we have lots of surgeries in the field, and many of them need mesh, and we see complications. And we are struggling to remove these, and especially true in my place, Tertiary Care Center in Dallas. We have a lot of technologies available, imaging technologies already available, but the problem is to define where the mesh is or where the sling is at times in scar tissues. And there has been some work done by John Delancey and his group to try to basically render these implants visible. And we're looking at a different way to look at that, which is improving our imaging technology and using advanced data processing methods to do that. So here's the example of what we're struggling with. This is an MRI with 3 different views, sagittal, axial, and coronal. And putting them together in 3 dimensions is really impossible, at least I can't. So the help of the mathematicians is to develop algorithms for us to be able to sort out where's the mesh and where are the relevant anatomic pelvic structures. If you take the slices on the MRI and put them together, you get a big opaque cube. That doesn't work. If you do transparency technologies, you withdraw images to see the key things. That doesn't work either. You're missing important features. The best technology they're offering right now is called image segmentation. And this is based on basically this follow-up process here, going from optical flow to training the machine, and then to bring that into a 3D slicer. So the machine learning can in fact recognize objects quite readily. They have a very high accuracy for a large number of objects. So picking up about 10 pelvic structures should be very doable for that technology at present. The problem is that you have to train the system, meaning thousands of images, and we don't have them because we don't have thousands of patients that we can import into our data set. So the proposed solution is here. What they're proposing is called optical flow, where you can see the same images progressively over time, and with modeling you can predict where the object will be in the next fraction of seconds. So they take basically 2 images and then they create lots of artificial images in between. So for example, here you'll see between slice 1 of this sagittal view and slice 200, and I won't run to 200, but with a little tweaking of the model, they can create some artificial images between the first and the second slice, and they can then import that into the model. So if you then manually segment that, you can determine in the front of these images where the pubic bone is, the bladder, the vagina, the rectum, and then you can figure out where that mesh equicolpopexy is located pretty accurately. And so they then bring this into a 3D slicers, and they make this beautiful rendering that they have here. So that part of the technology is straightforward. So there are challenges, because even though I tried to simplify it for you and for me, as a urologist not having any expertise in mathematical modeling, it's not a trivial task. That transformation process is complicated, and they have to satisfy multiple constraints and conditions. And they're also exploring other ways of doing this with smart fusion and multi-atlas segmentation, which are other techniques that they are using in their fields for image analysis. So here's basically the summary of the work in progress. So far, we've worked about 10 patients. We have recently gone to 20, and we're working into an NIH grant submission at present. Thank you.
Questions, please? Well, as a surgical gynecologist, I find your technique seems very, very valuable. With time, do you think you will achieve the speed to have dynamic pictures? This is static, as I understand you.
Yeah, it is static right now, but they can create as many images as they want. Basically, it's the mathematical formulation between slices that is the tricky things. So when you can basically create a flow, like, it's basically going from images to movie, creating basically lots of images in between, so you see something flowing. They can do the same with the technology. So you see an image, I see an image, they move to the next image, and in between they create a bunch of images which are extremely different, but very, you can't pick up the difference, but they can. And they can basically make that a dynamic process, yes.
Very interesting. So you think, because I think that it's not only for taking out some mesh, it could also be how does meshes change the physiology of the area?
Totally agree. Right now the focus is on trying to help with guiding surgeons, ahead of a reoperation. But you're totally right. We don't really know what happened to mesh in the body. So we don't have the opportunity right now to re-image a lot of patients, figure that out. We do ultrasound for that. MRI is a bit of an expensive technology. So right now this is more for surgical planning, but I think you pointed a very good other application. Thank you.
Thank you very much.